Hello, everyone, and welcome to week 2 or episode 2 of the Big Data Project for Crude Medwish. I am Neil. I am the project manager. And just a recap, we are trying to explore big data in a meaningful way. And I was asked last week about implications for this. And I actually made a really handy PowerPoint, which I'll show as soon as I just briefly explain what we did last time. That will elucidate the reasons why R is important and why this analysis actually is relevant. So a couple of you guys pointed out last time that you guys couldn't actually open this Excel file, and brilliantly enough, actually you need to use this little command right here, which is important, I've noticed. So yep, we imported some files, and I'll actually run the code and I'll explain it, kind of as it's going. So this statement right here, we just imported the data. I actually just changed my path name. Path is like the map to your file directions. I believe if you just look up how to find where your file is, I mean, you can keep in your downloads. I'm on a Mac, so it's a little different, but yep, so I put it there. I made a little code book. Not it improved it too much since last time, just because I didn't see the urgency. But if you guys really would like, I can add it as well. And you can actually Google this. So if you actually Google this LBXSTR space NHANES, it should come up actually in their code book, but you have to search up for every single one. And I have a list somewhere on my computer, but I use the ones that I remember off the top of my head and I actually used for my research at some point. So down here, we basically some descriptive statistics. So if you remember correctly, this basically is saying, I want to use this data frame, and this is saying, I want to run the following commands off the data frame. So this TBL summary is create a summary table, and we're going to organize it by MortStat. If you remember, MortStat is whether they're dead or not. So 0 means they're alive, and 1 means they're dead. 1 typically in statistics, and if anything biomedical, means usually the event happened. In this case, the event is death. And then for this one, I just add the p-value. I mean, if you remove this, simply this p-value would disappear. And then modify caption. It's like you can think of like adding a caption. It's like adding a table, like title caption, whatever you call it. And then for this one, just bolding the labels. So just want to make the left-hand stuff bold. And if you remember correctly, I added these 2 asterisks because if you don't have them, this title isn't bold. So a little nuanced. I had to Google that. I did not know the top of my head. And then we use this cool filtering command, which basically said, I want to go in this data frame, the 1999 patients, and I want to make a systole. I want all the patients who have a systole greater than 120, greater than 80. And then I run the same type of data table called table 2. So this console will just tell you any errors that happens as you notice. I'll just tell you off the top of my head. This is happening because there's not enough events for MCQ 180D, which I'm not really sure what that variable is. I think it might be age of diagnosis of a heart attack or something. It just means there's not enough events for it to be significant. So as you can see, we have a table. This is obviously the not filtered data. We have 8,290 people that aren't dead. And then one quick way to figure out if your command worked is if you go to the second table, which if you remember correctly should have less people because it's only people with hypertension, both systolic, diastolic, there should be less people. And as you can see, that's the case. You can see median age. That's your median, your mean age, and these are 95% confidence intervals, or you can think of it as your 1 standard deviation. Or I guess correctly, it's more 1 standard deviation, not your 95% confidence. And yeah, this means people who died obviously are older. That makes sense. That's significant. I'd hope so. You can go to the list. There's a lot of things. And one thing I want to say, which is really interesting, is KIQ 022. If you look into what that means, it's quite interesting that people on dialysis, a 1. So 1 meant they are on dialysis, 0 meant not applicable, and 2 meant no. I find it interesting that 100%, or sorry, 6, you know what I mean, 6% more than 0.7, so it's significant. I'm not an expert just yet, but yeah. Education level seems to, I guess it's not significant, but interesting. Income significant, looks like people with a lower SCS are dead more often. You can look more into this variable is. PP is pulse pressure. That's the focus of my research, and it's same for more mean arterial pressure. It's interesting, that this occurs, but that's a different story. But yeah, as you can tell, interesting trends emerge. But yeah, that's essentially what we did for these 2 commands. And then if we get down here, I'm not sure what actually through an error. I'm going to rerun this. I am very unsure why that's the case. I'm actually going to rerun that and see if that fixes the error. If not, that'll be a issue for next time. So I guess we won't use autoplot. Sometimes R does this, and I don't want to have to restart R and make the video any longer, so we'll just ignore that. But all the other commands actually should run. Awesome, looks like it did run. So essentially, this is creating a Kaplan-Meier survival curve, and I'm going to talk more about what that actually is today. It basically just tells you survival. It's a step function, and I'm actually going to blow this up so we can see a little bit better. It is a step function that basically tells you if it'll load. Sometimes R does this, so I'll just rerun it. Yep. Okay, maybe not today. So essentially what it is, it gives you a step function. In this case, it looks like a line because there's so many people, but usually it gives you a step function if there's very few people. It tells you survival. I'll go over more of it today, but that's what this code did over here. So essentially, this is what I call last video, if you want more information about it, the boring version of this. There's no colors and not enough details. It just tells you the bare bones mathematical function and graphs it. This next command graphs it, this one just creates it. Same thing here, this creates it, and I correlated it to or sorry, stratified the correct term, to whether or not they had this variable, this event, which, if you're interested, is whether they have congestive heart failure. The strata down here, no CHF, not congestive heart failure versus congestive heart failure, obviously is a significant by the p-value decrease in survival. And that's what this tells you. You can go over my last video if you want more details, but that's a brief overview of what happened. And today we're going to go over more survival analysis, but I really quickly want to actually go over some stuff. So Kaplan-Meier, its modeling is what this curve is on the left. And it basically, you analyze survival over a specified time period, 1, 2, 5, 10 years, etc., to assess survival probability. In this case, you can just take how many ever months there is, so 250 divided by 12, and that'll tell you how many years it is. So if you do the math correctly, this is over 20 years of follow-up, which is incredible. And this is actually what you want from a study. So for all the enthusiastic statistics people out there. So Kaplan-Meier does have its problems. So you see these vertical tick marks, and there's actually no change at that point in survival because the patients drop out of the study, which can be a very big, real problem. And basically, it means that you have no clue what happened to these patients. And just take my word for it, that this is straight. If we zoomed in far enough, you'd see it's actually straight. And I'll show you later in the presentation examples where it's straight, because they're censored or they've just left the study and you have no idea if they're alive or dead. And all the patients are assumed at the same survival probability, which means, like, you can't just say, I, Neil, have a different survival than you if we take the same medication. That's a little counterintuitive because obviously we have different bodies, we would take the medication differently, we'd react differently, metabolize it differently, whatever. That's an assumption. So most often this holds true, except when it doesn't, and I'll actually get into when it doesn't. And then a really interesting thing is the event happens consistently, as in, every time you take medication, if you're going to die, you're going to die. It's not going to be selective. Makes sense. So the survival probability for the mathematicians out there simply is this: the number of people living, died, divided by living at the start. And that's called S of t. That's each point, or survival probability. So I'm going to give you an example. This is actually taken straight out of the paper that's currently in my manuscript that I submitted to a journal. But this is a paneled figure. The captions something I added in later, but so we have on the left a survival function. I actually took away the 95% confidence intervals because it didn't look too nice. That's what these blue shaded stuff is. And I removed the grid lines, made the fonts pretty, etc. That took some time, but I definitely think if you play around with the command syntax, actually Google what the commands do. For instance, you can actually take away the grid lines, like no dot grid lines equals false or something of the sort. There's a lot of ways that you can go around it. Let's see what else. I made strata more, so I obviously had an event that is quaternary, or had 4 levels to it. So these are really powerful. P-value, I even have a little risk table here that tells you the amount of people, alive, dead, etc. And yeah, so what the base of my research is not important. What it is that you need to know is that the survival function is something that people genuinely use to research, and people can publish whole papers around survival curves. And on the right is what we're aiming towards. This is machine learning. This is why my paper got accepted. Hopefully not just that, but yeah. So this is basically random machine learning to tell me or readers what is the most important thing contributing to the survival of people with CKD or chronic kidney disease. And it appears that out of all the blood pressure variables, we have systolic over here and diastolic over here, seems like this marker pulse pressure is super important, which is, novel. Anyways, this is one we're more used to seeing with the 95% confidence intervals. And this was a survival curve generated from literally like thousands and thousands of people in this whole study, not just the N1999 data I told you. I generate this myself, so if you're gonna use it, please reference me. But yeah, similar survival, the strata. And then because people ask me about the biomedical engineering aspect of this, I actually took this from a paper, I believe, covering implants. I'm not really sure what implants they were for. I'm going to assume they were for hip and joint replacement, but I think they might be for something else. Yeah, so implants obviously are an engineering thing, but how do you know, if people with these implants are living longer, living less? You have to do a Kaplan-Meier. There's no way around it. You can't just say at the end of the study, oh, 10 out of 100 people lived. That literally provides no prognostic value. When you show the curve, you can see the change over time in survival, which sounds like it betrays the assumption, but it's not really, because this probability is a compounded event. Survival is also compounded. So think about you're multiplying the probabilities together. So that's what it appears that it's changing, but we see a little step function as each patient dies, etc. And this, you can interpret this however you'd like. It seems like probability of survival is about the same until there's a drastic drop off between this red one seems to be doing very, very well, this cemented reference. So I assume this is a control. And then seems like this green and brown are not doing so well. So this Mallory or whatever. And yeah, this is used for a whole lot of reaches. If you're in biomedical sciences, you're going to find a survival plot in any paper you read, unless it's just pure of something. Even animal studies have it. Everything will use a Kaplan-Meier survival plot. Trust me on that. I would be tempted to say, find me a paper that doesn't if it involves animal models, animal models or humans. And then a very, very powerful tool, which if you take any form of statistics and health sciences, or even if you become a graduate student, do the public health minor, I'm not trying to advocate for it, but for the public health master's program, you will be exposed to Cox proportional hazard ratios. So it analyzes these survival curves and tells me, what is the ratio of survival? What is the likelihood that this red line has a higher survival than the green line? Well, we can qualitatively say, it looks like maybe 33% better survival. These proportional hazards give you a quantified number. And by using really complex statistics, it can get super, super complex. It'll adjust for everything, meaning it'll take out the other factors. It'll say you want to analyze the treatment of survival, the survival between two groups treated with different implants that have, antibiotics and killing bacteria. It can basically ignore the effects of age, ignore the effects of gender, income, mental health, illness. It literally, if you provide the characteristics, meaning if you collect the data, so if you collect age, collect sex, gender, income, whatever, and you provide that into this hazard ratios model, it'll tell you, okay, we'll negate those effects onto survival, and then we'll see really whether your outcome of interest, whether it's the implant, the antimicrobial properties, whether that actually made a difference, or if it's simply based off, the two people had very different ages. When I say this is powerful, this is super powerful. And every single health sciences paper that deals with patients will and usually does use hazard ratios, or they use a very similar concept called odds ratios. I'm not very familiar with odds ratios and relative risk personally, and I think they're not as valid in most cases as hazard ratios. But usually it's a limitation of the data. So if you don't have time, meaning you don't collect patient survival over time, then usually you can't do a hazard ratio. So hazard ratio is the gold standard typically. So when you compare two groups and you run this hazard ratios, I'll show you through the code in 1 second. It'll tell if it tells you it's above 1, it means the second group, which is most often your experimental treatment group historically, is deleterious. So if it compared to groups, say comparing freshmen and senior versus graduating, no, that's a bad one. Comparing like freshmen and seniors on dining hall usage. It's a little not really survival, but I'll tell you why that's useful. A hazard ratio tells you the likelihood of the event of interest. So not always survival if that's your event. Like say your event is whether they go to a dining hall. And if I say comparing freshmen to sophomore, and if the freshman to sophomore hazard ratio is 1.50, that means that seniors more often than not go on average go to a dining hall 50% more than freshmen. And then if it was under 1, so if it was 0.50, it means that the seniors are 50% less likely to go to a dining hall. Interesting. Same thing for survival, just dining hall survival, just flip that around. So yeah, so we call it productive otherwise. And the assumptions are interesting, and it means hazard's constant over time, meaning you always have the same chance of dying to the event, at any time point given. And survival is different, meaning you have to have differences in the survival curve, meaning if these are not significantly different, if your p-value is, bigger than 0.05, that means you can't do a Cox proportional hazards and be confident in your results. And if you're interested, this is something taken from my paper. Again, I didn't actually use this. This is my supplementary data. And obviously, I've not recoded the variables in this case because I guess I just screenshotted from my raw results. But HR's hazard ratio. And let's say we have a non-continuous variable. Let's say we have gender. Gender, I guess I meant sex in this case because I'm using male and female. And I compared male to female, and it appears that your hazard ratio is 1.10, which means I guess that being a male is protective, if that's a better term, meaning your experimental group, you're female, if you compare male to female, is deleterious survival. And while I would just say that's really funny, it's not significant, thank God, because your 95% confidence intervals are super large. They actually go into the below 1 range, so you can throw out your result automatically, and your p-value is really large. So I'm not too familiar with confidence intervals. I'm not like statistics really good at it, but I can tell you that usually you can ignore the p-value if your 95% confidence interval does not go below 1. So in this case, mean arterial pressure looks like 1.0 to 1.02 with the middle 1.01 is your hazard ratio. Even though the p-value is not significant, most people would say, huh, that's pretty cool because it's all within the, it's all indicating that, hey, this is deleterious. But more importantly, since MAP, I'll tell you a fun fact, is a continuous variable, which means it's on a range from 0 to, I guess, hypothetically 200, 260. It means that for every 1 increase in this variable, there's a 1% increase in dying, which is really cool, actually, if you think about it. We keep going down here. These are all, zeros or ones. But once we get to like EGFR groups average, this is one I find very interesting. So this is saying it's a stage variable. It's a nominal, I believe, ordinal or nominal. I can't remember the term, but it has stages 0, 1, 2, 3, 4, 5, and 6. It says as the stage increases. So that's what this means. So 1.84 is like as it increases, you're 84% more likely to die every time, which is horrifying. But anyways, but yeah, that's what these mean. And now we're actually going to work on the code. So the code is actually a little more, I guess it can be considered complex. I personally don't think it's too bad, but sometimes you struggle with actually coming up with a code. So we're going to type this out. So we're going to name this first proportional hazards model Cox, because I can't come up with a better term. So Cox pH is the term we're going to use. And it's an actual term because this whole box comes up saying, hey, Cox pH, blah, 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 blah. So don't do what I did. Yeah, so Cox pH, and we're going to provide a survival model. So you can do a Cox proportional hazard analysis on any, you can do it even on a line if you'd like, but typically you do it on a survival model. That's what it says. Well, that's the survival function, but you get my point. So I've always copy paste the same code every time. That's because I'm lazy, but I'm sorry. Yeah. Okay. What did we just do? Well, it ran. We can see over here, Cox created. And basically what we said is run a survival analysis, and I want you to tell me whether BPQ-020, which I'll tell you right now, is whether you have hypertension, which is a 1, or you don't, which is a 0, whether that's important. So let's think, just thinking about it. If I have hypertension, am I more likely to die? Yes. So we should see a hazard ratio of above 1. And to figure out if that actually is the case, let's just run a summary. Oh, thank goodness. So let me find the term of interest that we would like. Yes. So you can just look at this, your experimental coefficient. That's, think about as your hazard ratio. We are using the raw code. So we can think of this as like what statisticians would see. We have a hazard ratio of 3.386, which is wow. This looks like you're 300 times more likely to die if you if you have hypertension. And the confidence intervals seem to agree. They don't cross 1. They in fact are very well above it. And the significance is, I don't even know what that number is. You can think of it as 2 times 10 to the negative 16th significance, which is extremely, it's basically 0 is what this model is trying to tell you. Interesting. But we never run pure hazard ratios, because remember, we never told it, hey, so in this case, we ran a Cox survival model, but we didn't adjust for age. We didn't adjust for like gender differences or anything. So let's actually do that. Why not? So I'm always a lazy coder. I always copy paste the last lines, and let's call this Cox age, and we'll do summary Cox age. We're going to change that, and then we're actually going to add age. So what do? We say BPQ020 plus age, and then let's run all the lines together. That's a little confusing, I guess. Let's just run the second line. So when we run this, we adjusted for age, right? Oh, well, what do you know? It looks like the hazard decreased because now it's factoring that age component. Because obviously, if you're older, you're more likely to die. But we also have to realize that when you're older, we also are more likely to develop hypertension. So it adjusts for confounding variables, which is extraordinary when you think about it. This statistics tool is incredible. It's been around for the last 60 years, but I think it's still neat to this day. Significance is maintained. It looks like age is a significant predictor. And since we know age is a continuous variable, let's look at what this means. It means that for every year you're alive, how do I interpret that? You're 8.8% more likely, so you just multiply by 100 for that. You're 8.8% more likely to die on average. And then look at that, your blood pressure, your hypertension variable decrease. It means now you're only 28% more likely to die if you have hypertension, which is, closer to the true value. Think of it as a limit. The more variables are correct, the more likely you're to get your true answer. But remember, there's something called overfitting or underfitting. So if you don't have enough population and you keep stacking on these controlled variables, you won't get significance, even though there is. So you need to do a power analysis before, and that's a whole other realm of statistics, which I don't want to get into because this is 100% not a graduate level class. Anyways, so Cox age, tells us, as expected. So what if we just did some basic covariates? I guess I've already created this, but just do as I do, copy paste, never hurts. So let's keep adjusting. I'm going to tell you a quick trick. I'm going to adjust for MCQ 160B, congestive heart failure, MCQ 160C, unstable angina, I believe, which is like, atrial AFib, I believe. MCQ 160D, which is had a heart attack before. Let's adjust for BMI, I'm sure we know what BMI is. Race, income, education level. I know it's gender, but it's sex. I'm sorry, I need to fix that. But so when we run this, what do we expect? We expect that hopefully it maintains the same thing. Oh, wow, would you look at that? So this is actually a gold mine for details. This says a lot. So it appears that the significant ones are, labeled with asterisks. So 2 just means it's less significant, but as long as it's 0.05, below 0.05, we usually take it. And even you'll see here, 0.1 can sometimes be your threshold. It appears that age, significant, blood pressure or hypertension significant, congestive heart failure significant. Unstable angina, surprisingly, it's not significant. Yeah, you can see, it looks like education level significant and endurance significant. So looking down here, we can see these coefficients. Remember that 160C or income are not significant. So as expected, until we get to BMI. So BMI, I'll tell you just a little fun fact if you want to do more research on this. There's something called the obesity paradox in research, which has shown that a lower as your BMI increases, they seem to be living longer. I say they, meaning people with a higher BMI, which is odd because this goes against every other thinking we know, which is usually as your weight increases, you have other things that may affect you, just, deleterious to your health. It appears that that is not what the research shows. And that's actually something I wanted to delve into, except there is no good way to answer that question as far as I'm aware with the statistics I know. And you'd have to do a case control study or like some type of study. That's for you guys to figure out. But looking more into the obesity paradox, you might find my advisor slash signer offer on my IRB. He's pretty well versed and well known in the field. And then we can see the gender is interesting. That means males are more likely to die than females. I guess that makes sense. Anyways, that'll tell you. So that's cool, but what if we wanted to, do stuff for the filter data? What if, remember, the filter data is people with hypertension. So that's up to you guys to figure that out. How would you do that? Remember that we said data equals this. That means that's the data we want to look at. So change it to the data frame you filtered and, answer your own research question if you so choose. So let's make the figures look more presentable. So how would we do that? Well, we're going to use something called GT summary, and I'm going to do this because this makes my graphs look pretty. And if you don't include it, I won't be mad, but I think they look gross if you don't add that command. It just makes the font tiny. So we're going to do Cox PH again. We literally just use this command up here, but let's just take. I like this one actually. We're gonna do this one, which has a lot. So we're gonna copy paste that here, and then we're gonna do the operator. I don't know what that's called, but I think it's neat, and it just is used to chain commands together. And we're gonna call the command GT summary, and we're gonna say : TBL summary, and then we're gonna. Oh, I apologize. We're gonna do TBL regression. Sorry, of course I have it with summary. Regression, and we're gonna say we want the exponent of our so x equals true is what do we call it? It's basically just generate it tells you the hazard ratio. That's the only good way I can say for it. At least that's what I think. Because when I don't include x equals true, it usually does not print out this hazard ratio. So as you can see, the table actually became smaller when I actually ran the GT summary compact. As you can see, it provides the same values, just in a table format if you want to make a table. So I hope that was helpful. Next week, we'll be delving more into machine learning, unless you guys want to go over studies and stuff like that. Thank you guys for watching. Let me know if you have any questions. You guys can make tables, explore the data on your own time. But yeah, I hope this was helpful. Email if you have any questions. And if you're interested for a more in-depth look in these medical statistics, feel free to email you with your ideas. I'm happy to provide any. And if you want me to explore other types of data, I can do some fluid dynamics or something. Anything that you guys are interested in. I want to cater to you guys. And from last time, I got a lot of advice to talk more about the applications more so than the code. So I'm really glossing over the code structure. Because in R, you don't have to be a coder. In fact, most people that use R are biostatisticians. So people who are not programmers, might I add. So be aware of that, I guess. So yeah, and please email me any ideas or anything you want me to go over, maybe even to reproduce figures or stuff or etc. And I hope this was helpful. Thank you guys for your time, and I hope fall break is as enjoyable as it was last year. Anyways, see you guys later.